Okay, so I want to talk about the sampling distribution of the sample mean and sample proportions today, and talk about the central limit theorem. The central limit theorem is an important result in statistics, and you can tell from its name, the central limit theorem. You know, theorems are important statements of facts in statistics, or actually in general. And limit theorems is a subclass of theorems that are more important than regular theorems because they are limit theorems. So central limit theorem means it's very central to those limit theorems, and that means it's even more important. So a central limit theorem, roughly speaking, we talk about X bar now, so a sample of random variables, and if you take that X bar, subtract its mean, divide by its standard deviation, that's going to be a Z, or standard normal. Same thing for P hat. If you subtract it, P hat is the proportion, so you start with a binomial distribution. Now you focus on not the number of successes, but the proportion of successes. You subtract the mean, that you divide by the standard deviation, or the standard error, and that should be that's a bell shape. And that's what the central limit theorem roughly says, provided that n, the sample size or the number of trials, is large. And this is a remarkable result because it tells you, starting with any distribution, uniform, exponential, whatever, if you average things correctly, and if you are interested in averages, and you have a large number of random variables, you're going to have a normal distribution. We already learned about normal distribution, so there are hundreds of distributions which we can even not know what they were, and just focus on the normal distribution, and that's why we did that. Okay, so let's start with the normal distributions. If I start with a normal distribution with mean, mu, and standard deviation sigma, I know if I take x, subtract mu, divide by sigma, that's going to give me the standard normal. That's what we did in the previous chapter. And I know now, for any distribution now, if I take x bar, if I take its expected value, or the mean of x bar, that's always going to be mu. So that's good. But x bar, if I take its standard deviation, that means the standard deviation of x bar is going to get smaller and smaller as n gets larger and larger, because it's going to be sigma over square root of n. And the sample is called the sampling distribution because x bar is done from sampling. We obtain it using sampling by picking samples. So the distribution of x bar is a normal distribution with mean, mu, and standard deviation sigma over square root of n. We summarize that by saying x bar minus a mu over standard deviation of x bar, or sigma over square root of n, is a z distribution. Okay. So now the question is, what is the sampling distribution of the sample mean x bar if x is not normally distributed? If x is bell-shaped, is uniform, say, or exponential? The answer is still x bar is still going to be approximately a normal distribution with mean, mu, and standard deviation sigma over square root of n, provided n is large. Large means here 30 or more. So that's how fast x bar converges to normality. Okay, and so to show you graphically what that means is, see if this works. So if I start here, say with something that's uniform, that's one sample. If I go to 5, maybe my sample, so for n equal 5, my sample would go up like this. But if I go, say, to 30 and equal 30, it's going to converge to normality, almost normal, very close to normal. Then I can use the normal distribution. Okay, now let's do an example here. Suppose you have a population with mean equal mu equal 4 and standard deviation 3, and I pick a sample of 36. So what will be the mean and standard deviation of x bar? And I want to do the second part also. What's the probability of x bar between 4 and 5? I want to leave those for you as an exercise. Let's see. So we have, let's summarize. N36 mu 4 sigma 3. Clear. So now I have n. I want to pick a sample size of 30 from a population x where the mean of x is 4 and the standard deviation of x is 3. Okay, so the answer, the first question is, what's the mean of x bar? And of course that we know from that formula it's the same as mu of x, which is 4. And the sample size we said is 36. What's the standard deviation of x bar? Now we know that sigma over square root of n, so that's equal to 3 over square root of 36. So that's 3 over 6, which is half. So therefore x bar is approximately, because n is more than 30, normal, with mean with mu of x bar equal 4 and sigma of x bar equal 0.5. Okay, the second question we have is, what's the probability x bar is between 4 and 5? So I want now, what's the probability of x bar between 4 and 5? So I know x bar is normal, so I can take the z-scores of 4 and 5. So what's the z-score of 4? z1, that's going to be 4 minus the mean of x bar, okay, divide by, I just want to emphasize that, sigma of x bar, because we're working with x bar here, not x. So that's going to be 4, is that 4? Yeah, minus 4 over 0.5, so that would be 0, and z2 is the z-score of 5, so that's going to be 5 minus 4 over 0.5, which is equal to 1 over 0.5 or 2. So now the problem now becomes P of z between 0 and 2. We've seen this one before, right? Yeah, so that's between 4 and 5. Okay, let's continue with this. Let me clear this. So I want P of z between 0 and 2, and remember we need 2 decimals for this. So I want to graph this. So if I graph this one here, I go from 0 to 2 here, and then I would go to the z table. I go to 2.0 here, and my second decimal is going to be 0, so this would be my answer, where I would read it from the z table, and that's going to be equal to 0.4772. It's point, so that's going to be what? 0.4772. That's the answer for this question. Okay. For proportions now, suppose the distribution of x is binomial with parameters n and p. What's the mean and standard deviation of, this should be p hat. I think I can fix that. Let me see. Yeah. Yeah, that's going to be p hat. And so the answer is going to be p hat. So the mean of p hat is going to be p, the original parameter, and the standard error of p hat is take pq over n and take the square root of that. So that's what we want, or that's what we have actually. So what's the distribution of the sample proportion? So this is really similar to the using the normal approximation to the binomial, except now instead of dealing with the number of successes, we're dealing with the proportions. So z is going to be, if I take p hat, subtract the mean of p hat divided by the standard deviation of p hat, that gives me a z. Because the mean of p hat is p, the standard deviation of p hat is the square root of pq over n, and I have to be careful to use that as my standard deviation, provided n is large. What does n mean, n equal large here? The same condition we had for to use the normal approximation, np greater or equal to 5 and nq greater or equal to 5. Remember, q is 1 minus p. Okay. So let's look at this quick example here. So if I have, it is claimed that at least 30% of all adults favor brand A versus brand B of something, like coffee or whatever. To test this theory, a sample of 400 is to be selected. So we're going to select this sample. We haven't selected it yet, but we want to test it, but we want to study the probability. So we know that somebody claims it's 30%. And suppose in the sample we're going to have, of course, X individuals will prefer brand A. So if I summarize my data, N will be 400, P will be 0.3, and my proportion of successes is going to be X over 400. I want to call that P hat. Now I want to find the mean and standard deviation of the sample proportion, provided that the claim is valid. Suppose that claim is valid, what can we tell about the sample we're going to select? So that means the mean of P hat is going to be P or 0.3. The standard deviation of P hat is going to be P square root of PQ over N, or 0.3 times 0.7 over 400, or 0.023. Okay. So now if I pick my sample, because it's extremely unlikely in the 400 I would get the proportion of those who would prefer brand A would be exactly 0.3. But if the claim is true, for the proportion to be between 0.27 and 0.33 should be fairly high, maybe over 80% or 90%. Otherwise that claim would not be true. So that's basically what we're looking for. So what should be that probability? And that's what we want to calculate. So what the probability that P hat would be between 0.27 and 0.33? So that gives me a margin of error of 3%. So we're going to talk about that later on. So now I know that P hat, NP and NQ is going to be more than 3, because N times 0.3 is more than 5, and N times 0.7 would be more than 5. So I can use my central limit theorem and convert this into a Z problem. So first I need the z-score of 0.27 and I need the z-score of 0.33. So let me see if I can go back to my tablet, edit this, clear, and now I have, what do we have? We have n equal 400 and we have p is 0.3. We have the mean of p hat is equal 0.3 and we have the sigma of p hat is 0.023. That's how we calculated that, and we're trying to calculate the probability of p hat between 0.27 and 0.33. It doesn't matter whether we use equality sign here or not because everything is continuous now. So I need the z-score of 0.27 minus 0.30 over, remember I want to divide by the standard deviation of 0.023, and that was, we computed that negative 1.3, so that's here, negative 1.30, and z2 is going to be the same thing, 0.33 minus 0.30 over the standard deviation, which is 0.023 or 1.3. Is it 1.33 or, yeah, 1.30. And so now my problem becomes probability of the z-score of z1 negative 1.30, p hat is z, and 0.33 is 1.30. And so if I graph this here, oh, that's a sketch, my 0, negative 1.30 and 1.30. So I want to find this area, which would be twice the area between 0 and 1.30, so twice this area. So if I go to the z table, if I go to the z table here and go to 1.3, my second decimal is 0, so that would be equal to 4032. That's going to be 0.4032, and so I want to double that, so that would be 0.8064. That would be my answer to this question. So I finished this problem for you. I want you to do this if it's 2, 5 and 3, 5. So now my margin of error is a little bigger, so my probability should be a little bit more. And I also want you to repeat these two questions if my sample size is larger. If we have money to pick to sample 800 items, opinions of preference here, and assume that this still will be the same. This will get much smaller now, and then those answers would be much higher. Okay, so I want you to pause, do these questions, and see what answers would you get. Just repeat what I did here in all cases. All right, thank you.